So welcome back to Physics 1060, How Things Work. Things that I didn't say last time in introduction, pretty good for those of you who are new to the class since then. Anyway, Lou Bloomfield, and this is How Things Work and that stuff. I have a paper version of, abbreviated version of the syllabus over here on the chair. The real version lives online on a website that I run out of my office. So this will link you to that or point you in that direction. It's also the Colab site links you to the real site for the class. The point of pointing out that the website's there is I put videos of each class. This video that you're seeing over here being recorded at the moment, I put them online. I put them on YouTube and then link them to the schedule page for this class. So that schedule page that's printed out here is actually a live page that evolves with time as we get through material faster or slower than expected, generally slower. Anyway, you'll find the video link there shortly after each class once I get it up on YouTube and you can watch the class afterwards. Or if you miss a class, if you try to go into like online learning mode, fine. It's a slippery slope, though. A lot of people sort of drift away if they stop, oh, I'll watch it later. It's always later. All right? Anything else I want to say? Any questions that you have about getting started in the class and so on? The first assigned work isn't due until a week from Wednesday. I need to put it up on there's a homework website that I run also out of my office that I'll put it up on, and I'll point you in the right direction, and I'll try to do that in the pretty near future. All right, other than that then, back to talking about skating, and within skating, the world of inertia. And in talking to people after class, and I want to commend you all for both asking questions during class and for showing up after class to come play with stuff. Talking to people after class, there are a bunch of situations that we talked about regarding inertia that are just tools for a living, things that you ought to know. So if you take nothing away from this class, other than ideally some skills at thinking, some issues of physics that are useful. Inertia is really useful. You already use it without even thinking about it for various things. I'll either remind you or I'll inform you. I don't know which. But the first trick I did, right, the first demonstration was pulling a tablecloth out from underneath place settings. There are 1,000 situations like this. And if you can't get up the gumption to try pulling a real tablecloth out from underneath place settings, just any old stuff sitting on a sheet of paper. If you want to get the sheet of paper out, you can sit there and push all the coins away, or you can just take the sheet of paper and pull it very fast. If you do that, the coins don't move. Why not? Because like everything else in the world, they exhibit inertia. Inertia is a noun. I don't know whether it's a concept. It's certainly not a physical quantity. You can't measure inertia exactly. But it's this observation about the things in the world that if you leave them alone, that is, don't push or pull on them, they tend to keep doing what they were doing. Doing what they're doing means they keep the same motion. If they're at rest, they stay at rest. If they're moving, they move steadily. And that's where we're sort of working at the moment. So the coins stayed put because it is their nature. They exhibit inertia. They are inertial. If I pull quickly, if I pull slowly, you know the coins are going to follow the sheet of paper. Why? Because of friction. I will not be leaving the coins alone, air quotes, right? If I go fast, I can defeat that problem by, there's still friction, and we'll talk about friction down the road. But what I can make it do is act for such a short period of time that it has almost no ability to change the motion of those coins. So they just sit there. And out comes the stuff. So you can do this. You want the paper, if you still read papers, and they're under a whole pile of books. Yeah, you can move all the books. Or you can just grab the newspaper and just give it a nice quick snap, and it'll just come right out from underneath them, and the books will just stay there. And if it doesn't, and if it breaks your favorite such and such, don't sue me. Any questions about why that works? The second one I wanted to show you. Are we down to? Oh, another one. I knew I had a second one. Is, you injured your arm, it's taped up, and you just spilled something, you have to have a paper towel. Well, you can either go there and tear it off the complicated way, or you just take the towel and just, well, almost right. But you get the basic idea. You've done this, I hope, all your life. You just snap it. What are you doing? You are trying to exert as little, you're trying to leave the roll alone. That is, let it be inertial. You're going to exert a force on it. There, I used the word I didn't mean to use, but you're going to pull on it. But you can do it for such a short period of time, it has almost no influence. So you can just yank off sheets. I've got to recover my, still trouble. All right. Not all demonstrations work, and usually the ones that fail are more fun. Okay, third one, which I got into this last semester and discovered that a lot of people don't know these tricks. They're not tricks in the sense of magic. They're tricks like ways you can use physics to make your life easier. Toothpaste isn't the perfect example of what I want to show you, because if you're down to the last dribbles of toothpaste, you can get them out of the tube by smushing the tube. But there are an awful lot of fluids, liquids in nature that are in your life that come in containers that you can't squish. And suppose your container of shampoo is down to the last little bits, and they're in the bottom of the container, and the top of the container is far away. How do you get them to go to the top of the container so you can get the last bit of shampoo? You throw it away and then go buy a new one. But there's another way. If you're in a hurry, use inertia. Get the entire container moving quickly, and then stop the container, not the contents. The contents. So what I do? Just snap it like that. What I'm doing is I'm actually successfully getting all the toothpaste to the cap. What's the physics of this? You get everything moving, and now it's all inertia. Hey, we're moving, look, this is great. And then you stop the plastic tube, and the contents, hey, we're moving, inertia, I love inertia, I love inertia. It keeps going. And it moves until it slams into the cap of the container. So, can you follow that idea? Container of ketchup, or your favorite sauce, whatever it is. You're down to the last little bit. It's in the bottom of the container. You got to get it to the cap. How do you do that? Get the whole thing moving, and then point the cap. Make sure the cap is at the leading part of the motion, and then stop the container. And the liquid just merrily moves. Inertia, inertia. I love inertia. Up to the cap. Okay? Hopefully that will, if that's not new to you, you can go, oh yeah, I don't know that, but at least you can name why it happens. If it is new to you, hopefully you'll be using this rest of your life to get 10%, 20% more of whatever it is that they sell you. And Heinz can come after me as undermining their income. All right? Any questions? I think I'm done. All right. So, what I was showing you again, that things behave this way. When we observe them, you get them moving, they keep moving the way they were moving. There's a name for this behavior, or there's the name is inertia. There is a law describing this behavior. It's long since acquired the name Newton's first law of motion. And this is a primitive version of Newton's first law. And we'll see, I got two more renditions, the last one being the final version. Newton's first law just simply states formally this observation we're having about inertia, that an object that's free of external influences, in other words, left alone, moves in a straight line and covers equal distances in equal times. So if you watch it go, you take a video and you measure, you discover it's going straight and true, and it's covering equal distances every second, for example. I put in this, that in yellow, that the idea that a motionless object is also obeying this law. It is moving at equal distances and equal times. They just happen to be no distance. Physicists do this all the time, where we take a special case that sounds like it doesn't fit the story, but we define it as fitting the story. So I am currently moving, but just not very much, 0, okay? It is what it is. So that's a simple version. To give you a better version of Newton's first law, I have to develop some language in this class. I mean, some of you have seen these words before, but we'll pick up some new language for some of you. I already asked you this question last time, and let me just rehash it because it was interesting. When you first thought about trying to cut grasses with a rotary lawnmower, it seemed unlikely that you would be able to cut those grasses if nothing held them in place, i.e. roots. And by the time we had gotten done, all of you had come to the opposite conclusion, that you don't have to hold the grasses in place to cut them with a knife or a sharp blade. Inertia alone will do the job. It is their nature to stay put, and you can just sneak the blade through them. And this stuff shows up all over the place too. I mean, an example that I won't fully do is I can just throw this thing in the air and karate chop it. You can break it. There's no problem breaking a stick like this. I mean, it might hurt your hand, so I won't do it because I value the stick and my hand. But you don't have to hold it to slice it. Inertia will tend to keep it in place, and you can do all kinds of nasty things to it. Well, inertia is just, it's just trying to obey this concept of inertia. All right? Anyway, on to other things. So to develop the language for Newton's first law, we can look at the skater and characteristics of the skater. So a skater, first off, a skater's got a location where the skater is. The official name for that is called position. So the position of the skater. So let me pretend to be the skater. If you want to, for a physicist to say where I'm located, to be able to write it down, to be able to say it on a telephone, it turns out that you've got to convey a couple of pieces of information to the reader or the person on the phone to know really where I am. And those pieces are 3 of them, essentially. One of them is a reference point that you're going to use to indicate where I am relative to that reference point. So, because if there's no reference point at all, you see, you got nothing to start from. So my usual starting point, sorry for those of you who heard me do this before, my usual starting point is right between these 2 monitors. That's the reference point. We'll call that sort of location 0, position 0 actually. So you can say somebody up on the phone, you say, he's at position 0, that pins down exactly where I am. They have to know what position 0 is, but beyond that, we're good. In addition to position 0, the definition of it, to tell the person where I am, you need 2 other pieces of information. One is a distance, how far I am from position 0. In this case, 6 feet, about 2 meters. Units, we can get lost in units, but hopefully you have some sense already for what units are. Feet is a unit. Meters is another unit. They're both units of distance. This is a meter for those of you who are fuzzy on the concept. It's a little over 3 feet. Anyway, I'm about 6 feet from position 0. That isn't quite enough information yet. There's one more piece necessary, and that piece is direction. I'm 6 feet from position 0, directly south. That's about right. This is about south of that. So that is enough information. At that point, you say, he's 6 feet south of position 0. The person on the other end of the phone knows exactly where I am. Is that okay? That kind of a quantity. So position is a physical quantity that tells you where things are. It's technically known as a vector quantity, which immediately, the word vector, maybe some of you are totally comfortable with it. I can think back to when I was in college, it was a little like, oh, what's that? It's not a big deal. A vector quantity is more than just an amount. Your weight is an amount. How much cereal you ate by volume is an amount. Position has an amount and a direction. The amount is 6 feet, the direction is south, and you need them both. And they just go together as a team, and that team arrangement is called a vector. Is that okay? Or questions? Yeah. Can either of those have negative values? So, thank you. These are great questions. Is vector quantities, if the amount becomes negative in a vector quantity, so he is now minus 6 feet south of that position, where would I be? Where do you think I would be if I were minus 6 feet south? Exactly 6 feet north. I'd be there. So vector quantities have this neat characteristic that when the amount goes negative, the direction flips. I should say, 6 feet north of position 0 is the same, exactly the same, as minus 6 feet south of it. Is that okay? Yeah. Fiona? For what reason would you use a negative amount? I'll give you a preview of something we're going to encounter pretty soon. Toward the end, for those of you 1050, you've seen this exact story, and we'll hit it in a couple of days. And I'm going to move along to the right, carrying with me an interesting physical quantity, a physical quantity that's characterized as a conserved one I have to carry, that I can't destroy or produce out of nothing. If I've got it, I've got to carry it with me. That quantity is called momentum. So you've heard of momentum. We will, in the near future, pin down momentum nicely, I hope. Okay, so I'm going to carry momentum with me. I have to get it from something because you can't make it or destroy it. I have to get it. So I'm going to get it out of the table. Now I've got it. I'm carrying momentum. And momentum is a vector quantity too. My momentum is to your right. I'm now going to give my momentum to the wall. Boom. Okay? So far, nothing interesting beyond, okay, I walked to the wall. But I picked up momentum from the table. I carried it with me and dropped it off. Specifically, I carried momentum to the right. Let's say 10 units. I don't know, whatever the units are. Okay, so I was carrying 10 units of momentum to the right. I'll do it again, but this time I'm going to give it to the wall and then some, okay? I'm carrying 10 units of momentum with me. And I can't stop moving until I get rid of them. I'm going to give them to the wall. Oh, I gave the wall 20 units of momentum to the right. I'm now running a deficit of rightward momentum. I have negative 10 units of rightward momentum. What's that the same as? End of story. I was carrying 10 units of leftward momentum with me as a result. I gave more momentum to the wall than I had. I ran a deficit, which is the same as having positive amount in the other direction. Is that okay? The fact that vector quantities flip nicely in this manner. If you give away more than you have of momentum to the right, you end up with momentum to the left. It works seamlessly and easily. Is that okay? The details of all that momentum, yeah, we'll get there. But it is useful, the fact that vectors can flip like that. Okay, so position, we got position under control, I hope. Any questions about position? How about if your position is changing with time? That's characterized by another physical quantity known as velocity. Velocity is the rate at which position is changing with time. And because a change in position like this is quite different from a change in position like that, velocity is also a vector quantity. It's got a direction to it. For those of you who know calculus, it is literally the time rate of change, the derivative of position with respect to time. So I'm not going to, if you don't know calculus, don't worry about it. Just notice that if my position is not changing, my velocity is 0. If my position is changing like this, my position, every second, I'm about 1 foot closer to the wall. So I have a velocity of 1 foot per second to your right. End of story. Is that okay? It's a vector quantity. It's got a direction, of course. This is 1 foot per second, about. to the left. Those are quite different velocities, so it does matter that you have the direction in there. The amount part of velocity has a name you're very familiar with. It's called speed. So my speed in both cases was 1 foot per second. But my velocities were different because the velocity it's fancier than speed, not just because it's kind of, well, I'm a sophisticated guy, I talk about my velocity. No, it's not just that, it's that velocity carries the second piece of information with it, direction. So, is this a big deal? No, it's just speed and velocity are not identical because velocity has the extra bitty to it, direction. Is that okay? Anything else I want to say? Okay, so it turns out that a skater who is experiencing no external influences, something we've got to come back to, moves at a steady pace in a straight line. We can reword that. They're moving steady pace, that means the same speed, in a straight line, that means the same direction. Same speed, same direction, that's the same velocity. So a skater who's not being pushed on moves at a constant velocity, or just constant velocity, leave the out, leave the article out. Constant velocity. Is that okay? So the second version of Newton's first law, just a little reworded, says an object that is free of external influences moves at a constant velocity. So it's a fancier way of just making the observations about the world of inertia. Okay. Any questions about what velocity means and how to observe it? I should point out that it takes one glance to observe somebody's position. You just look, you see it. You know, you can say their position. He's 6 feet south of the special point. Okay. To see velocity, you have to glance twice. You go blink, and then a moment later, blink. Oh, he moved. And you can kind of look at the change in position and the amount of time between those two glances. You get velocity out of that. So 2 glances for velocity. We'll come to something down the road shortly where you need 3 glances. All right. What else? Okay. So on to another physical quantity, the third in the series, force. A force is a push or a pull. It's just a fancy name for it. I mean, Star Wars is back, so there's the force. This is real. This is physics force, not like woo force. So it's a fancy name for a push or pull. So if a skater is being pushed, they're experiencing a force. If they're not being pushed, no force. And forces have influences on objects' motion. Ultimately, because an object, a skater, if one person pushes a skater to the right, nothing else is pushing on him, the skater's their motion's going to evolve toward the right. If 2 people are pushing on the skater, one to the right and one to the left, they're fighting over the skater. The skater may experience some change in motion, but basically it's in response to some composite of those two pushes. So, long and short is people can't respond to all the individual forces acting on them. Instead, they respond to the sum of those forces, where direction is taken into account properly, which is a non-trivial task. You know that if 2 people grab my arms, suppose I'm on ice, no force, I'm just going to stand here all day. I'm going to be an object at rest, staying at rest. If one person pulls me to the left, whoa, I'm going to start to move to the left, right? One person pulls me right, whoo, to the right. If 2 people pull me, and they pull equally hard, there's going to be no effect. I'm just going to be here feeling uncomfortable. If 2 people pull me sort of one that way and one that way, I'm going to do something in between. So that process that I would just hand wave through is the idea of adding up the forces, taking into account their directions, which is you're summing vectors, vector sums. And you may well have done vector sum type stuff in previous educational experiences. We're not going to do much of that because that's another way of spending hours doing stuff that finally you're unlikely to use. So just recognize that objects respond, as we'll talk about the response, to the sum of the forces acting on them, which is given the name the net force. That's the vector sum of all the individual forces. Okay? So, having done that now, we can finally do Newton's first law right. And Newton's first law says that an object that is not subject to any outside forces, or alternatively, that is experiencing zero net force, moves at constant velocity. This is a formal statement that describes inertia, this idea of inertia. If an object that's experiencing zero net force moves at constant velocity. And moving at constant velocity is, I call it in common language as coasting. So stuff that's left alone, that's free of forces or that's experiencing no net force, coasts. So I can't push one of these little pucks. I put so much junk on the desk here. Got nowhere to work. Okay. If I push one of these pucks and get it started, and then we watch it, it skids to a stop. And you might say, well, an object that's left alone stops. And that actually is what people thought for thousands of years, that if you don't push on it, it stops. If you push on it, it moves. If you don't push on it, it stops. But the problem, where that comes from, that's friction. You haven't sort of thought deeply about friction yet. If we get rid of friction, which I can do approximately by turning these little guys on, they've got a fan inside that lifts them off the table. Now, once I get it started, which is before the story, now it moves straight until it hits the coins. It moves at a steady pace in a straight line, namely constant velocity. That's coasting. So coasting is coasting is the movement of an inertial object, an object that is free of external forces, or zero net force. Is that okay? So, if Aristotle had had these things kicking around, he might have had a different sensibility. He was in part responsible. Well, there's junk on the floor, but for the idea that you have to push things to keep them moving. I will say a few more words about that. This observation that an object that is left alone moves at constant velocity is harder to get into your gut than it seems. Your intuition says that when you push on things, they move. And when you don't push on them, they stop. I know you can hear my words, but and you go, no problem, I got that. But watch the world around you and make sure that you've got your gut. You really feel it. The person bicycling by you, and they're going steady pace, straight line, they're coasting, they're inertial. They are experiencing zero net force. Make sure that you sort of internalize that, because it's not what you experience so often, because you so often experience friction or air resistance or things that mess up the simplicity of that story. All right? Questions? All right. So skaters do a lot of coasting. Yeah. If you've got zero net force and you're coasting, would you still have a velocity? Yes, and the velocity would be constant. So the hallmark of coasting equals constant velocity. Those are the same exact concept. And a coasting object experiencing zero net force or being inertial, it's all the same thing, that is moving not because something is pushing it, but because nothing is stopping it. So the motion in one of these, in my inertial stories, the motion starts before the story starts. So I get going, now the story starts, and I keep moving, not because something is pushing me during the story, but because nothing is stopping me. I brought in the motion at the beginning of the story. I was already moving, so I have to keep moving until I stop. And I can even do a little preview of this. Why? Why do things keep moving? Why inertia? It's actually got to do with momentum. The fact that when I started the story, the momentum I brought up ahead of time when I said, oh, I'll show you negative vectors. When I get moving, not only do I have velocity, but I carry something with me, momentum. And I can't stop until I get rid of that momentum. So the reason things keep coasting along is really because they're carrying with them this crazy stuff, this momentum. They're burdened with it until they get rid of it. Daniel. Why do planes need to keep their engines on when they're already going 300 miles an hour? And they actually are coasting. So a plane is going along at a steady pace, straight line, 300 miles an hour, 500 miles an hour, real fast. What's the situation there? Well, it is inertial. They are inertial. This plane I just described for you is inertial. It meets all the requirements. It's traveling at constant velocity, or equivalently, it's coasting, or equivalently, it's experiencing zero net force. Okay? So it's really doing that. And the devil is in the details of that zero net force. Well, it's experiencing terrible air resistance. Well, substantial air resistance. So it is being pushed backward by the ambient air. And that by itself would slow it down. However, it's using its engines to get some of the air to push it forward. The details there, it's throwing the air backwards, and the air then pushes it forward. So it is simultaneously experiencing a slowing air resistance and a forward push from the air because of its engines. And those cancel perfectly. So it is inertial. It's experiencing zero net force, but there's a lot of complications in the zero net force. And the same is going on with a bicyclist. I mean, to bring it down to earth, make it simpler. A person bicycling along a straight line at a steady pace. What's going on there? They're inertial, they're coasting, but they're experiencing air resistance and a forward push from the ground with their pedals. So those two cancel. Or if I don't turn on the gadget here, I just push. It's inertial right now. What's going on? I'm pushing it to your left. The table, by way of friction, is pushing it to the right. We cancel each other, and it coasts. Is that okay? I mean, it's a little bit, I realize even as I'm saying this, that internalizing that and all is like, it's a little complicated. But there are lots of things, lots of situations where there are multiple forces acting on one object. But if they all sum to zero, the object is inertial. And it does what inertia has in mind, coasting. All right? So I've got two more physical quantities to bring up in the context of skating. We've got a skaters moving at constant velocity, which is fine. It's kind of boring. If you happen to be in a race, I can't even make a silly story out of it. Okay, it's kind of limited. So what do we want to do? We want the skater to be able to start and stop, turn, other things like that. Those all involve motion that is not coasting. If you're slowing down, your velocity is getting smaller, the amount thereof. If you're speeding up, your velocity is getting greater, the amount thereof. If you're turning, you're also changing your velocity, because remember, velocity has direction to it. So any of these things, speeding up, slowing down, or turning, they all involve changes in velocity with time. And the name for the physical quantity that describes the changes in velocity is called acceleration. So again, for the people who've had calculus, acceleration is the time rate of change of velocity. It is the first time derivative of velocity. As simple as that. Again, don't worry about it if you don't know physics, don't know calculus. Let me show you some accelerations. I've showed you position. This is position, I'm here. Or alternatively, I'm here, okay? I've showed you velocity. So this is now my velocity is non-zero. I'm heading to the right 1 foot per second, and you can see this. You have to look twice to see it. You have to look, I'm here, and then you look again, I'm here, and now I'm running out of room. So velocity takes 2 glances. You watch the position change with time. All right? Acceleration is the quantity that describes the changes in velocity with time. Things like speeding up, slowing down, turning. So now you need three glances in principle to see acceleration. I'm going to accelerate to the right. So you do glance 1, glance 2, glance 3. There's a bigger gap between the first 2 glances, second 2 glances than between the first 2 glances. So evidently, I changed my velocity during those times. So far, we're okay? Seeing velocity is hard. You've got to look, in effect, 3 times. In fact, you sort of have to watch the thing to see whether a car is accelerating, a person is accelerating, a bicycle is accelerating, a bird is accelerating. You've got to watch their movement. Are they moving? Yeah, sure, okay. Is their moving change? Is their movement, as in their velocity, changing with time? Ooh, that's a little more subtle. And distinguishing the physical quantity that is velocity from the physical quantity that is acceleration is hard. I know that from, I've done this, I've taught this class for a while, okay? And I know how hard people struggle to get those 2 straight. Let me show you, I can illustrate with various situations. I should point out that acceleration and velocity do not have to be in the same direction. They can be opposite one another. They can be at cockeyed angles to one another. They all have, there's meaning to all these arrangements, and they have clear consequences. So let me start, I will show you my acceleration with my hand. This involves doing multitasking, something I'm extraordinarily bad at doing. So I'm going to try to move around and show you, velocity is easier to see, but acceleration is harder to see. So I'm going to show you acceleration. So right now, no acceleration. Now acceleration to the right. I go faster and faster. Now no acceleration. I'm going to coast. Now I'm going to do acceleration. This is a weird one. I'm going to do acceleration to your left. Now it's triple multitasking because now I'm having to talk and whatever. Yeah. Too many things at once. I also have to think, which doesn't have, that's hard. You can probably smell the wood burning. The point of this is what? That if I accelerate in this direction, I begin to pick up speed in this direction. I go faster and faster and faster. Now I'm coasting because I'm not accelerating, but I'm still moving. I ran out of room for my story. Okay. So I'm going to accelerate to your left. Yeah, that's the third multitasking, is trying to remember my right is your left. Okay? It's too many things. So I'm going to accelerate to your left. I'm picking up speed. Faster and faster. I would say, go right out of the room. Woo! Okay. I'm still here. You can still hear me. Okay. I'm coming back in. Woo! I'm Colbert. Yeah, okay. So now there are situations where acceleration and velocity are in the same direction, like this. End of story. There are situations when acceleration and velocity are in opposite directions. Not yet, not yet. I'm going to pick up speed. Now I'm going to accelerate to your left. Whoa! And you notice during the initial part of this, I'm heading to the right, but I'm accelerating to the left. That's fine. It happens all the time. It often has a special name. It's called deceleration. That's just a special case of acceleration. When you accelerate opposite your velocity, so the vector of velocity and the vector of acceleration are opposite one another, we give it a special name. We call it deceleration. So I slow down, and if I stop accelerating right when I come to a stop, I become motionless, velocity 0, and I can stay there. But if I continue to accelerate, now I begin to pick up speed in the opposite direction. I'll stop, okay? Getting a sense of acceleration? Before I forget it, if I accelerate not in the direction of my velocity or against it, I can do weird things like I'm going to accelerate to my left. Let me get started first. Okay, now I'm started. Now I'm going to accelerate to my left. Whoa, I go in a circle. My velocity's this direction, but my velocity is changing toward the left, which bends my path. So this is also acceleration. And if I stop, I coast. I have to go back. Oh, coast. All right. Got it? it will take, for many of you, some of you will get it immediately, just, I mean, people are different. Some of you will struggle with it for a long time. Hopefully I've given you laid the groundwork for things in any case. All right, so a skater can move inertially, in which case she coasts, straight and true, steady pace, ting, ting, ting. If she speeds up or slows down or turns, she is accelerating during those moments. And nobody can do that without help. You cannot accelerate unless something exerts a force on you. Forces cause accelerations. More technically, carefully, net forces cause accelerations. Again, because you can't respond to each individual force acting on you. It's the sum that affects you. So when something pushes on you, the skater, and there's nothing else around, you accelerate. The extent to which you accelerate, which is to say how quickly your velocity changes with time, depends on the measure of your inertia, which is given a name. It's another physical quantity. It's called mass. And in my story today, it's the only one of the 5 physical quantities that is not a vector. Mass is just an amount. So mass, I think of it as, okay, it's the measure of an object's inertia. It's also the resistance of an object to acceleration, how hard it is to get it to change its motion. And you have a gut feeling for that already. If you want to take a little ball and I'm going from right to left, or right to left to right. I'm changing its motion, specifically its velocity, back and forth. Each of these changes involves acceleration, and it's easy. So this guy's got a little mass. It easily undergoes changes in velocity with modest forces. In contrast, the bowling ball up here, it's much harder, okay? It fights me a lot more. It's got a much bigger resistance to acceleration, which is the same as having a big mass. Mass has a unit that's familiar to you. Again, about units. There's the American set of units, which include things like feet. And then there's the SI, or metric, set of units, which includes things like meters. The unit of mass in the American system is some crazy thing. I don't even know what it is. I never use it, obviously, because I don't know what it is. The unit of mass in the metric or SI system is the kilogram, something that you do have some sense for. A kilogram measures how hard it is to accelerate something. We'll talk a little bit about later on about issues of weight. Weight is not a unit of mass. It's actually a unit of force because it has to do with gravity. So get rid of gravity. Mass is still there. It's how hard it is to make something accelerate. And you go up to different skaters. I mean, how would you figure out mass? You go up to a whole row of skaters. They're all sitting there on their skates, on their cell phones, of course. And you go up and you give them individually a big shove forward. That one. Okay? The big, beefy folk barely accelerate. You give them a shove, nothing much happens. Big mass. Okay? The little pipsqueak there on my first cell phone. Shoo, off they accelerate like crazy. Okay? They got a little mass. I know I rag on cell phones. Sign of the times. Okay? So acceleration, mass. Any questions about basically position, velocity, acceleration, mass, and force? Okay, so Newton's second law brings these together. This is one of the few laws which I think you should know. And partly because the concept is so already, I've already said the concept. It's not a big deal to write it down as a formula. It's the observation that forces cause acceleration, specifically net forces cause acceleration. Mass resists acceleration, and so an object, a skater's acceleration, is equal to the force exerted on that skater divided by that skater's mass. That's all it is. It happens to be quantitatively true, to the extent that I mean, modern physics has its complications to throw in, but setting aside some of the details of things like black holes and stuff, no, they're cool, but not the part of the story. This is exactly right. If you find an object, determine its mass, exert a force on it of a known amount, you can predict exactly what its acceleration will be. The force divided by the mass, nothing else. Is that okay? So when you watch the skaters going around the rink, if they're picking up speed, knowing their mass, you can figure out how much their acceleration is going to be given a force. They're all related to each other. And this is the underlying equation or relationship. Is that okay? I write the Newton's second law in this form, the traditional way of writing it down here, which you may well have seen it in or even abbreviated to. F equals ma, that's surely familiar to a huge fraction of you. F equals ma, wow. First off, we're assuming F is force as opposed to finagle, I don't know. Is that a pH? Anyway, whatever. There are always these stories floating around among physicists of things like, I wrote a test with an object of mass F, just to confuse people. Anyway, the conventional way of writing this equation is F equals ma, which puts force on one side, mass and acceleration on the other, and in my view, totally entangles those things. And there's no transparency to this equation. It's confusing cause and effect. I believe it's done because it gets rid of the division. That division there is evidently offensive to a lot of people, so they do that. This, in my view, writing it this way, which is just an algebraic rearrangement, which I certainly hope you can recognize and do yourself, putting the mass over on the same side as the force puts cause, the force fighting the mass, on one side and gives you the effect, namely the acceleration. So I guess it's my personal pet peeve, but I convey it on, or impose it all on you. All right? All right, what else here? So given that, I've got a bunch of cans up here. I could have a student do this, but I'll just, if I want to have, I'll actually put them on their sides so they can roll. This gets rid of friction. If I want to identify which ones are full and which ones are empty, what can I do? Come on, guys, stay put. There, okay. How many think that the way of figuring out which one's full, which one's empty is A, compare the velocities. How about B, compare the positions? How about C? How about D, consult the Ouija board? How about C, blow on the cans and observe its acceleration? Yeah. Right? The light ones, I should be careful. The ones with almost no mass respond, they're all getting about the same force. The ones with almost no mass, because they're empty, accelerate easily. The full ones, not so much. This actually is a practical observation, in the line of getting ketchup out of the tube. If you are in a situation where you've got rolly carts, some full and some empty, and you can't see inside them, as is typical at an airport, the carts carrying luggage, you want to figure out, and you can't pick them up to in effect, weigh them. They're too heavy no matter what. If you want to figure out which one's full, which one's empty, what do? Shake them. Give them a push. The full ones, because they have so much mass, will not accelerate much. The ones that are empty, because they have very little mass, will accelerate much more effectively. So you can use this. It's a tool for a living. All right, we'll continue on Monday.